the topic of solutions, I want to talk about families of solutions. Essentially, we can use all of these same ideas we just talked about to write our function phi a little bit more in depth. Maybe phi depends on some parameters or constants that we call C1 through Cs. So if there are S of them, we would say that this capital Phi here is an S parameter family of solutions to the ODE, or nth order ODE, I should say, on I, if it's a solution regardless of the values of C1 through Cs. Let's take a look at a quick example that will come up in the next section. So foreshadowing here. Let's look at the differential equation y double prime minus 2y prime plus y equals 0. Now I claim that the function capital Phi of x, c1, and c2 is a two-parameter family of solutions to this equation where phi is equal to c1 e to the x plus c2 x e to the x. Let's take a look. Notice I've got y that shows up. I've got y prime, so I need that. And I've got y double prime, so I'll need that. If I take phi prime, remember x is the only variable. Sometimes we might just write phi prime of x even though I've got constants floating around. Sometimes if it makes sense to remind the reader that this has parameters in it, you may see it written this way. Some authors also like to separate their variables from their parameters with a semicolon like this. I will use these notations kind of interchangeably. So the first derivative, this guy is straightforward. It's just c1 e to the x. Over here, though, I've got to use the product rule. I will get derivative of the first guy is just c2 e to the x plus derivative of the second guy is just e to the x. So I will get c2 x e to the x, or to simplify that, I get c1 plus c2 e to the x plus c2 x e to the x. And we can follow that pattern, by the way, to quickly write down phi double prime of x. Notice that the first coefficient I added to the second coefficient. So I'll get c1 plus 2 c2 e to the x plus c2x e to the x. Now when I throw these guys back into my differential equation, do you notice I am really taking phi double prime minus 2 phi prime plus phi. What do I get? Let's look term by term. I've got 2c2 minus 2c2 plus 0 c2 e to the x. So that's 0. Again, for the first terms, they all cancel out. Now let's look at the x e to the x terms. I've got c2 minus 2 c2 plus 1 c2, or that's 1 minus 2 plus 1 is 0 c2 x e to the x. So every term actually ends up canceling out. And do you notice it didn't matter what the values of c1 and c2 were? Phi still reduced this equation to an identity. Moreover here, phi is defined for all values of x. And because there are no x values that ended up remaining in this equation, we can actually say that this is a solution for all real numbers. Again, remember that the interval together with the function is the two-parameter family of solutions to this differential equation.